Hey, I'd like to welcome everybody here today to today's webinar on the calibration-free supersaturation assessment and control for the development and optimization of crystallization processes. My name is Mark Barrett and I am a Senior Research Development Engineer from the Solid State Pharmaceutical Cluster within Ireland. The Solid State Pharmaceutical Cluster aims to support the pharmaceutical manufacturing, commercialization and research industries in Ireland through collaborative research projects, upskilling and training programs. Our academic members from the cluster bring a wide range of expertise from solid-state material science to organic chemistry to the optimization and scale-up of crystallization processes through PAT. This is greatly complemented by our industrial partners who bring a wide range of expertise and knowledge from pharmaceutical manufacturing, commercialization and research. More information can be found on the website below. So the work presented during this webinar has just been submitted for publication to Chemical Engineering Research and Design, and hopefully will be published early next year. So we felt that mid-IOR as a technology was certainly underutilized with respect to crystallization, optimization, development and scale-up, certainly from an industrial perspective. So these calibration models, which are very well defined within the literature, have yet to transfer into the daily development of crystallization processes within industry. So hopefully we have produced a more qualitative method which is a bit more rough and ready, but certainly enhances process understanding with respect to supersaturation assessment. The new crystallization development platform at UCD combines two new EasyMax ALRs from Mettler Toledo with a Kaiser Raman and Mettler Toledo IOR and FBRM. The major benefit for this installation has been the combination of all PAT and ALR technologies on one software platform. So we can run all this technology off one PC and see a shift in our IOR or Raman signal with a shift in temperature or agitation. This has really increased the efficiency of collecting, but importantly understanding and interpreting the data. So really has enhanced our crystallization understanding within our lab. And for us it's been key to the development of this supersaturation methodology. So this is the platform we use at the bench scale, and then we do some scale up assessments to say a 1 or 2 liter lab max. So just jumping to our presentation overview, we'll initially look at why supersaturation assessment is important and also identify why we looked at alternative strategies for collecting this information. We'll then go through some experimental results looking at some supersaturation process maps and how we develop crystallizations by minimizing the cycle time while maintaining maximum particle size. We'll also look at some supersaturation assessment during tech transfers, and finally look at supersaturation control or open loop feedback control by using mid-IOR to control supersaturation to a specific set point. So initially let's look at why we assess supersaturation. So why is supersaturation so important? So supersaturation is incorporated into the kinetic equations for crystal nucleation and crystal growth. So therefore supersaturation will dictate the levels of or particulate size one achieves from a crystallization process. So obviously on scale, when supersaturation profiles shift, we obviously see a difference in crystal nucleation and growth observed. Hence crystallization scale-ups and tech transfers can be quite challenging. So your dissolved concentration can really dictate numerous crystallization characteristics. Levels of incrustation, agglomeration, your fines production, particle size, phase separation or oiling out, your polymorphic form, purity profile, and obviously your nucleation and growth kinetics. So really supersaturation is of the utmost importance, and really understanding it can aid in crystallization optimization and development. But really we've seen that this is not always the case. People don't always look at supersaturation. Maybe because of its ease of measurement, FBRM is looked at extensively, but really when you combine the dissolved concentration via IOR with the solid phase via FBRM, like completing the mass balance, you really have a full understanding of the limitations or benefits of your crystallization process. So really, for us, over the last number of months, has really increased the speed at which we develop crystallization systems. So shown here on our y-axis is concentration, and on our x-axis is temperature. So these are the standard sort of solubility curves, let's say, of our stable and metastable form. So if we cool from an undersaturated environment to a region where we're now supersaturated with respect to both forms, now our supersaturation, once nucleation is initiated, decreases as a function of decreasing reactor temperature. So obtaining this type of information gives you huge realm of opportunity for optimizing your process, be it for isolating the metastable or stable form, or for optimizing particle size. So although this information is hugely advantageous in developing crystallizations, it's not always exploited. So I'm just going to introduce a couple of slides that maybe explain why this technique is not always used. So I call this slide Supersaturation, the complexity of measurement. I've also included here on the right numerous literature references who go into specific details about the quantitative approach for supersaturation assessment via calibration models. I'm just going to briefly outline them to maybe highlight the calibration and statistical experience that's required for building these calibration sets. So step one would be to take spectra at known concentrations and associate a shift in the IOR spectra to a specific concentration. So essentially you have to build up a memory bank. So when interpreting the IOR data, you're able to associate a shift in IOR spectra to a specific concentration. So shown here by the X values would be typical concentrations that one would make up and take an IOR spectra of. So as you can see, you can take spectra across the entire solubility curve to ensure the accurate quantitative assessment of the IOR signal. So this can be time consuming, and sometimes you can't measure the values that you'd typically obtain in an experiment, as the time to measure can be, say, up to 30 seconds, where if you prepare a supersaturated solution, due to the kinetics, the system may only stay in the liquid phase for maybe up to 10 or 15 seconds, obviously based on the kinetics of the system. So this can be pretty difficult and pretty time consuming. Step two will be to statistically validate your PLS chemometric model. So this can be fairly intricate, and there can be numerous statistical challenges involved with the PLS method. Recently there's been the development of some noise filters to take out spectral noise. So obviously the combination or extension of these PLS models can become fairly complicated. So we say you need statistical experience and knowledge of chemometric methods to do this, and if maybe you're unaware of these techniques, this can be pretty complex and pretty time consuming. And I guess the whole idea of the black box is that ideally you want to understand the mathematics and the statistical numbers behind the calibration model, but maybe people don't always have the time to look at these. So step three will be to do the experiments and then to calculate the supersaturation based on the outline model. And as you can see, this is the information that I would output. So there's a number of steps prior to getting to step three that can, there's a lot of areas there where people can fall down, and maybe this was probably the reason why it's not really used in the daily development of academic and industrial crystallization processes. So let's now look at the newly developed peak height supersaturation method. On the y-axis we have a single peak height specific to the solute or API, and on the x-axis we have temperature. So now we simply heat from the isolation temperature, let's say 4 or 5 degrees, to your starting temperature, for example 40 degrees, and now we obtain a solubility curve in terms of peak height and temperature. So the next step would simply be to do the actual experiment, be it a 1 hour cool down, a seeding, or a 15-hour experiment, and just overlay that peak height trajectory over your solubility curve. So now immediately we have some relative or qualitative supersaturation information that we can assess to optimize or troubleshoot crystallization processes. So the important thing to note is that these profiles are prone to temperature effects if the spectra is affected by temperature, and this is typically why people do calibration models to model out that temperature effect. But we feel that it has no real bearing on the outcome of the development of these crystallization processes, and that this qualitative information that really enhances process understanding and development. So the big thing for us again is that there's no statistical validation or chemometric experience required, and this may be a more rough and ready technique that for the daily development and troubleshooting of academic and industrial crystallization processes that can be used both in the lab and at the plant scales. So let's now look at developing supersaturation process maps with the specific goal of maximizing particle size in minimal process cycle times. So what we're going to do here is we're going to try to determine solubility information prior to doing our supersaturation experiments. So obviously for this method, identifying a peak height specific to the API or solute is critical. So for this case study, we're going to look at a model system, benzoic acid. We have numerous API systems, one that's actually going to be incorporated into a publication. But for just for ease of use, we're just going to talk about benzoic acid. So what we do here is we have a background, a mid-IOR background in our ethanol and water, so our solvent mixture shown here in grey. We then spike in some benzoic acid, which then dissolves, and now we can identify, we take a sample, or an IOR sample, and we can identify peak heights of interest, so regions which we could track as a function of time and temperature. So as we can see here, at 1275 wave numbers, there's a peak that's unique to benzoic acid that is relatively high with respect to the rest of the spectral region, and its absorption is it's fairly narrow peak. So preferably we'd like to look at regions outside the realm of the solvent, but that's not always a necessity. So now let's assess dissolution via FBRM and IOR. So again, this is really the power of eye control, and it really lets you do this in situ. So what we have here on our primary y-axis is peak height of our solute, and our secondary y-axis we have our FBRM fine core counts per second. On our x-axis we have our reactor temperature. So as we increase our reactor temperature going from left to right on our x-axis, you can see there is a decrease in our FBRM fine core counts measured per second. So that obviously corresponds to dissolution. So as we dissolve our solid, we increase the liquid phase concentration of our solute. So that corresponds to an increase in our peak height. You can see our peak height plateaus at a point which corresponds to the dissolution of or disappearance of our FBRM or core counts, so disappearance of our crystals. After this point, we see a corresponding decrease in our peak height. So what we can show here is that the decrease in our temperature or decrease in our peak height corresponds to the temperature effects in the spectra. So as you increase the temperature of a liquid, the bond energy associated in that liquid decreases. Therefore, as mid-IOR measures that bond energy, there is a corresponding decrease in our peak height. So this is something just to note, but again, if we're aware of this prior to doing any supersaturation assessment, so again, we can interpret in our results. So now let's look at some differing cooling strategies for the isolation of this product. Shown here on the y-axis is the benzoic acid peak height identified in the previous slide, and on our x-axis is our reactor temperature. So what we're going to do here is look at different cooling profiles. So from a 1 hour linear cool down to a 1 hour cubic cool down from the saturation temperature to a simple 15-hour linear cool down. So again, we're going to look at the effect on the dissolved concentration or supersaturation and the effect on our particle dimension via FBRM to try gain an understanding of the limitations or benefits of this process. So our 1 hour linear cool down experiment is shown here. So you can see our peak height trajectory picks up a metastable zone width of approximately 4 or 5 degrees. There's then a rapid decrease in our peak height at the onset of product nucleation. Important thing to note here is actually from say like between 5 and 9 degrees C, there is a constant level of supersaturation throughout the batch for the rest of the experiment. So again, there's no accumulation or sudden decrease in product supersaturation. So that's something to note as we go forward. So now the next experiment we're going to assess is a cubic cool down from the saturation temperature. So as you can see from this plot, at approximately 14 or 15 degrees, the apex of the peak height, the apex corresponding to the full dissolution of the product. So what we'll do here is cool to 15 degrees and then initiate a cubic cool down. So that, as you can see here, the cubic cool down, because of its slower initial cooling rates, reduces the metastable zone, but importantly it reduces the bulk supersaturation between temperatures of maybe 12 to maybe 7 or 8 degrees C. So again, this reduction in the bulk supersaturation should favour conditions which will minimise product nucleation and prompt particulate growth. A thing to note here again is that we do not increase the levels of bulk supersaturation towards the isolation temperature, so we're not actually increasing relative supersaturation past the values obtained for the 1 hour cool down. So this is important behaviour because we're actually cooling quite aggressively towards the end of this batch here. So there's no real difference. So again, I would be confident that the dissolved concentration will be go to product growth. So again, this is where FBRM is very important because it allows you to assess these profiles as a function of time or temperature. So now the next experiment we'll assess is the 15-hour linear cool down. So again, with a reduction in cooling rate, we have a reduction in the metastable zone, but importantly, this system desupersaturates straight to the solubility curve, and then we desupersaturate along the solubility curve to the isolation temperature. So bulk supersaturation is minimal throughout this experiment, so again, particulate growth will be expected to be favoured. So as you can see, this method sort of opens the door for assessing different cooling strategies, but importantly we can use it now to derive optimal lab or plant supersaturation trajectories, and also for control set points for doing direct feedback control. So now let's look at some FBRM data. So looking at our FBRM no-weighted distributions, which emphasize the fine material, and our square-weighted chord length distributions, which emphasize our coarse material, we can see as we reduce levels of supersaturation by shifting from a linear 1 hour to a 1 hour cubic cool down, we reduce the number of fine particle counts observed per second, and we also increase the number of coarse particle counts observed per second. Furthermore, when we really reduce levels of supersaturation in the batch by desupersaturating along the solubility curve, we significantly reduce the number of fines and increase the number of coarse particles observed per second. So again, this is really showing the favourable attributes of combining qualitative supersaturation profiles with FBRM assessment. As we have a full understanding now of the mass balance, we can really design crystallization processes around this information. So again, this is just showing here the annotation, the reduced fine end and the increased coarse end of the chord length distributions. So what we wanted to do now was, we have a system that has very large particles, but this takes 15 hours. So can we take this information and design a process that will take 1 hour? So can we improve our cycle time while maintaining large particle size? So from previous knowledge of our supersaturation process maps, we knew that the smallest metastable zone obtained from the 15-hour linear cooldown experiment provided optimal nucleation and growth conditions. It should also be noted that the large or relatively large supersaturation values obtained for the 1 hour cubic cooldown and the 1 hour linear cubic cooldown attributed to product growth and not nucleation. So we knew we didn't have to follow the solubility curve to initiate or to prompt particulate growth. So what we wanted to do here was to reduce supersaturation throughout the batch by having a seed bed in place. However, we said that seeding wasn't permitted as it wasn't filed. So what we did was we designed a self-seeded process. So a self-seeded process is where you don't artificially add seed, but you generate your seed bed by cooling into a supersaturated environment and allow your process to desupersaturate to the solubility curve. So shown here is the supersaturation trajectory of our self-seeded process. So you can see here we cooled to a known or predetermined supersaturation level, which corresponds to the 15-hour linear cooldown. We then held and allowed our system to nucleate and desupersaturate to the solubility curve. At this point we then started cooling at a cooling rate of about 0.8 degrees centigrade per minute. Now this cooling rate was dictated to ensure that we isolated our product within the 1 hour cycle time that we deemed as being favourable. So importantly here, again, we have more information to play with, as we now have quantitative information that tells us that the desupersaturation of the product takes 22 minutes. So again, if you're trying to define hold periods for seeding, like isothermal hold periods, or for aging, you can really define that via your supersaturation, which again is very favourable. So the important thing to note here is that the supersaturation, which is accumulated after the hold period, is pretty similar to what we observed from the 1 hour cubic cooldown and the 1 hour linear cooldown. So immediately looking at this supersaturation process map, I would be confident that the increase in supersaturation from the solubility curve will be attributed to product growth and not nucleation. So in fact this is exactly what happens, and shown here is the FBRM chord length distributions, the no weighted and square weighted for the self-seeded process and the 15-hour cooldown experiment. So as shown, we can actually very similar particle size or particle dimension is obtained from the two supersaturation trajectories. But the big thing is that we reduce our cycle time by over 90%. So again, with respect to lean manufacturing and process optimization, the IOR and FBRM certainly combine together to give us to achieve this goal. So PVM really shows this shift in particle morphology, and as well as SEM images. So here's our 1 hour cooldown experiment where supersaturation was at its highest. We now go to a cubic cooldown experiment where we reduce bulk supersaturation throughout the batch. So again, you can see the increase in particle morphology obtained for the benzoic acid. The 15-hour linear cooldown experiment was actually pretty difficult to observe via PVM because the particles were so big. But again, you can see a much broader dendritic crystal for this supersaturation trajectory. And going to the self-seeded process, you can actually see the particle morphology and size is very similar to that achieved in the 15-hour linear cooldown. This again is confirmed by SEM, showing the shift in the particle surface properties, again going to something that's much bigger and maybe a little bit more favourable to that observed in the 1 hour cooldown experiment. So again, this really highlights the importance for us as a laboratory in combining bulk supersaturation and product dimension information via IOR and FBRM, as this really allowed us to design and understand an efficient crystallization process. So looking at these crystallization processes a little bit closer, we can see on the y-axis here we have our relative supersaturation, so that's our actual peak height minus our solubility curve, and on the x-axis we have a normalized process time. So what we assess here is the trajectory or differing trajectories of the 15-hour and the developed self-seeded process. Looking at the 15-hour experiment in black, we can actually see the relatively small supersaturation at the time of nucleation, and then the desupersaturation to the solubility curve, which in turn produces relative supersaturation values of approximately 0. Looking at the grey line, we can see that we cool to a supersaturation level of 0.015. We then hold for approximately 20% of the cycle time to facilitate product nucleation in this supersaturated environment. We then hold for an additional 30% of the cycle time to allow for the desupersaturation of the product to the solubility curve. This is then followed by the rapid cooling at approximately a normalized time of 0.8. So importantly, we're able to show here that maybe for 50% of the batch we are holding, and then for maybe 15% of the batch we are actually cooling to crystallize the majority of the product. So it just shows with the preparation of a self-seeded bed, and if you're careful and allow the desupersaturation to the solubility curve, you can actually cool very rapidly towards the end of the batch. So again, here you can see the inflection point in our supersaturation profile, which indicates the increased cooling of 0.6 degrees centigrade per minute. But the important thing is that that increase in supersaturation was attributed to particle growth and not secondary product nucleation. So jumping back to our presentation overview, let's now look at some supersaturation assessments during tech transfers. So understanding and controlling tech transfers and scale-ups. So although be it a very small scale, we actually performed these tech transfers within the EasyMax, going from volumes of approximately 40 mils up to maybe 120 mils. Although very, very small scale, we wanted to demonstrate the application of this methodology for assessing tech transfers or for troubleshooting crystallization processes. So what we did here was we assessed the tech transfer of a 1 hour crystallization of benzoic acid. So again, just a model compound. Again, we have our solubility here on black, showed expressed in terms of peak height, solute peak height, and temperature. And the first experiment we performed was a low volume with a Rushton turbine. So Rushton turbine, obviously having 6 blades, we have quite a high power input per unit volume in this system. So you can see again the supersaturation trajectory in this experiment. We have a metastable zone of approximately 4 degrees, and like previous experiments, we have this sort of very sudden desupersaturation of the product, and then a constant supersaturation after a temperature of say 8 degrees C. We now transfer this system to a higher volume, so something of approximately 100 mils in volume, but now we have a 4-bladed pitch blade turbine. So obviously our power per unit volume or turbulent mixing efficiency will dramatically decrease. So again, we're trying to mimic the type of tech transfers observed on plant. So now if we perform this experiment, we can see that the previous experiment had a metastable zone of approximately 4 or 5 degrees. Now the tech transfer achieves a much larger metastable zone width, and much higher supersaturation values are achieved throughout the batch. So again, this can lead to maybe the nucleation of unwanted polymorphic forms, or the reduction in particle size, oiling out, agglomeration. There's lots of things that could go wrong. So let's say for this example, we wanted to achieve a more constant supersaturation below the supersaturation profile obtained from the blue peak height. So what we do here is we actually seed it at saturation and cooled rapidly. So now we can see that we achieve a constant supersaturation via seeding and aggressive cooling to maintain a low supersaturation even with the higher increase, or even with the higher batch volume and the reduction in turbulent mixing efficiency. So again, this is just sort of showing things, methodologies that can be assessed by looking at your dissolved or supersaturation throughout your batch. It really sort of increases process understanding with respect to troubleshooting. So now looking at FBRM, we can see now that the low volume well mix system produces a nice uniform coordinate distribution. We then shift to the left, so we increase the number of fines present in the crystallization by increasing the level of supersaturation observed during the tech transfer. We then reduce supersaturation during the tech transfer by seeding. And as we can see here from the chord length distribution, we notably reduce the fine end and extend the coarse end. So we've dramatically increased the particle dimension observed by seeding and maintaining a constant supersaturation. So again, we just wanted to highlight here, it's a qualitative method, but it does open the door for really assessing and troubleshooting crystallization systems, particularly when we're looking at tech transfers and scale-ups. So now let's look at using mid-IOR peak height values for maintaining specific supersaturation set points, so by means of open loop feedback control. So understanding and controlling tech transfers and scale-ups. So on transfer or scale-up, there's an appropriate shift in your heat transfer and turbulent mixing capabilities. So in turn, supersaturation, and as a result, particle size or polymorphic form could be affected. So what we wanted to do was to stress test our crystallizations within a laboratory environment to understand how our profiles must shift, like our cooling or our anti-solvent addition profiles must change on scale when a difference in heat transfer or mixing capabilities is encountered. So what we initially do is to scale our system from a 70 ml EasyMax to a 1 litre LabMax environment, and we assess supersaturation and FBRM. So shown here on our y-axis is our solute peak height, and our x-axis we have reactor temperature. So as shown previously in our webinar, we can now express our solubility curve in terms of peak height and temperature. Now, if we overlay our 1 litre experiment with no feedback control, we can see there's a substantial increase in the metastable zone, but importantly there's a notable increase in supersaturation throughout the batch when compared to the supersaturation profiles derived at the 70 ml scale. So again, this accounts for the shift in turbulent mixing and heat transfer capabilities that we encounter higher supersaturation levels throughout the batch. So a notable problem with this batch was the poor flowability of the product. So the vessel nearly gummed up, and product incrustation was also encountered. So what we wanted to do was we wanted to use mid-IOR as a feedback control tool via the iControl, LabMax iControl software platform to maintain supersaturation throughout the batch to, let's say, a predetermined value of, say, 2 degrees, maintain a metastable zone width of 2 degrees C as we desupersaturate our batch. So in this case, as I mentioned, our set point is 2 degrees C, as this was deemed favorable from previous EasyMax supersaturation experiments. So now let's look at our IOR feedback control conditions. So our strategy for feedback control would be to assess our solute peak height in situ by means of IOR, like we did in previous benzoic acid case study. We then calculate a supersaturation set point and compare it to a desired or predetermined value. This calculation then alters the reactor temperature to maintain this supersaturation set point. So the important thing to note is that all these calculations are hidden within the iControl LabMax user-defined trends. So you can calculate these all within the interface within iControl. So this actually, this calculation occurs every 6 seconds. So this iteration, so a change in our reactor temperature is calculated every 6 seconds. So, you know, we're using this to control supersaturation, but we're also using it to control particle dimension by means of FBRM. And also at the moment we're looking at for direct feedback control to control the polymorphic transformations of APIs. So there's numerous applications to feedback control, but for this case we'll just look at mid-IOR. So shown on this slide in the red dotted line is the supersaturation set point, which we predetermined to be 2 degrees centigrade. Shown here in blue, although which looks pretty complicated, is the supersaturation feedback control. So I'll step down through this blue profile now to identify what each step means. Step 1, like we did in previous case studies, was an initial self-seeding. So we cooled to position 1 and held until product nucleation and growth was observed. Step 2 was define dissolution control via FBRM. So we controlled our fine particle counts to below 150 counts per second by implementing a slow heating rate at step 2. Then at step 3 we implemented our supersaturation feedback control via IOR peak heights. So as we can see at step 3 we immediately obtain or go to the supersaturation set point of 2 degrees centigrade until a temperature of approximately 7.5 degrees C, where there's a slight consumption of supersaturation. It should also be noted that we no longer achieved this 2 degrees centigrade supersaturation set point due to the faster dynamics of this crystallization. It simply just did not allow us to cool fast enough to get back to this supersaturation set point. So again, the important thing to note here is we can derive optimal profiles to give us a specific supersaturation trajectory that may be associated to an optimal particle size or to the isolation of a specific polymorphic form. So what we'll look at now here is our relative supersaturation here on the y-axis and time on the x-axis. So as we can see here, looking at the grey dotted line where no feedback control is implemented, this supersaturation profile is a function of the scale up, so the change in heat transfer and mixing capabilities. We can see we almost double the relative supersaturation throughout the batch. And again, this led to excessive incrustation and poor product flowability because of small particle size. In black again, we'll look at our feedback control. We can see initially at point 1 we have our self-seeded process. Then at point 2 we control the dissolution of the fine particle counts below 150 counts per second. And then at step 3 we implement our feedback control to control supersaturation or relative supersaturation to 0.01. Again, we can see the slight consumption of supersaturation after approximately 50 minutes, and then the desupersaturation of the product at about 75 minutes. So again, this just sort of manipulation of the previous graph shows the substantial reduction in supersaturation throughout the batch. And again, we can definitely highlight the increase in process understanding, as we now have a direct understanding that scale or heat transfer and mixing will directly affect product size, flowability and supersaturation. So now we have a means to control that. So now looking at complementing our supersaturation information with FBRM, we can see we substantially reduce the fine end of the chord length distribution and increase the coarse end. So we have dramatically increased the particle size or particle dimension. Again, this would probably be shown experimentally by the better product flowability for this system when we controlled supersaturation. So again, it's a real positive attribute of doing feedback control, as we can essentially control particle dimension on scale. An additional thing that can be assessed is creating polymorphic design spaces via this supersaturation assessment. So what we'll do here is obtain similar solubility information for both our stable and metastable forms. What we have here is our peak height on our y-axis and our temperature on our x-axis. So what we can see here is our solubility of our stable form of an API, and now the solubility in terms of peak height and temperature of our metastable form. So the great thing about this is now we can design experiments around supersaturation to ensure we never become supersaturated to the undesirable metastable form. So what we've done here in green is an experiment where we have cooled at 0.5 degrees centigrade per minute, which was the maximum plant cooling rate. And as we can see here, we never become supersaturated with respect to the metastable alpha form. So again, now with confidence I can say that we can scale this process at that cooling rate, based obviously on a favorable particle size, but we will always ensure the optimal isolation of the stable form. So again, it just gives you means for assessing optimal cooling or anti-solvent addition profiles. So obviously the important part of this will be to combine this supersaturation with FBRM for particle dimension assessment, but also with Raman and PVM to ensure the pure isolation of the stable form. So looking through some webinar conclusions, firstly I hope to have shown that this qualitative supersaturation assessment facilitates the development of process maps where outputs like particle dimension or polymorphic form can be optimized in minimal cycle times. So again, with respect to lean manufacturing for defining isothermal hold periods for seeding or isothermal ages, like this supersaturation assessment really gives a quick, attainable method which could be used for the daily development of industrial or academic crystallization processes. Secondly, we certainly iterate the importance of combining this method with FBRM assessment, because really looking at the dissolved concentration via IOR with particle dimension via FBRM really facilitates a quantitative understanding of the limitations of tech transfers and scale-ups. Also, we used this supersaturation method for devising feedback or open loop feedback control for maintaining supersaturation throughout crystallization batches. Again, this gives us a great opportunity for stress testing our crystallizations within a lab environment to assess the effect of decreases in turbulent mixing and heat transfer efficiencies that typically will be observed on plant. So again, we can understand how to shift our addition or cooling profiles prior to actually going to larger scale reactors. And then finally, we looked at extending this methodology to the creation of polymorphic design spaces. So looking at strategies for the isolation of the pure stable or metastable forms. So prior to going through some acknowledgements, I'd firstly like to outline this 3-day hands-on crystallization development and optimization course we are currently running at UCD. This course couples the hands-on use of the latest PAT technologies such as FBRM, IOR, Raman, turbidity, pH and PVM, coupled with the latest ALOR technologies from Mettler Toledo such as the EasyMax and the LabMax systems. So we go through the typical design and optimization strategies for crystallization systems, from the three-dimensional solubility design space assessment, so understanding the limitations and benefits of cooling, anti-solvent and reactive systems. We then extend this information to the quality by design or optimal design of particulate systems with respect to particle size or polymorphic isolation. We then finally couple this information with direct feedback control via PAT and with other computational software packages like CFD and Dynachem to facilitate right first time tech transfers and scale-ups. So this course has been running over the last number of months, and certainly would be interested to hear from anyone who is interested in attending this course. Please feel free to contact me on my email address below to obtain more information about this course. So finally, to some acknowledgements, I'd like to thank you all for attending this webinar. Hopefully you found it useful. I'd also like to thank Professor Brian Glennon for his direction throughout this work, and also to Dr. Hong Sung Hao for his continual support within the laboratory. I'd also like to thank all the PhD students, with particular reference to Morchi McNamara, who helped me put this publication together, particularly with the development work on a particular API. Finally, I'd like to thank my colleagues at the Solid State Pharmaceutical Cluster, both academic and industrially. And finally, I'd like to thank Ben Smith and Rule from Mettler Toledo for making this opportunity possible for presenting this work. So I'd like to break now to take some questions on any of the work I've presented here today. If we don't get to answer any of the questions during this Q&A session, please feel free to contact me on my email address provided. And finally, thanks again for attending this webinar series.